All right, welcome everyone. So today we have Jose Polo-Gómez from the University of Waterloo speaking about no black holes and light. So he's a PhD student at the University of Waterloo in the group of Eduardo Martin Martinez, and he's known for his work on measurement in quantum field theory and entanglement harvesting. And so today he's talking about this interesting recent PRL on the impossibility of forming black holes from light. So when you're ready, Jose.
Thank you very much, Jermaine, for the introduction. As Jermaine was saying, today I wanted to talk about no black holes from light. This is a work based on a PRL that I wrote in collaboration with Álvaro Álvarez Domínguez and Luis Garay from Universidad Complutense de Madrid, and my supervisor, Eduardo Martín Martínez. Without further ado, I'll just start. The beginning of this story is the fact that massless fields can a priori form structures held together by gravity.
This is because is your screen still shared? Oh yeah, never mind. Yeah.
Is it?
Sorry,
yeah, it's all right.
Yeah, very good. No problem.
Yeah, as I was saying, the beginning of this story is the fact that because it is energy and not mass, the one responsible for carving spacetime in general relativity, massless fields, and a priori form structures that are held together by gravity. So, for instance, we would be able to form structures that are held together by gravity with photons, even though photons in principle don't have mass. Yeah. So the first person to examine this possibility was Wheeler in 1955, and he called these structures, these electromagnetic structures held together by gravity, gravitational electromagnetic entities, or GEONs for short. Then afterwards, there were some follow-ups in which people also considered this possibility for the almost massless neutrino field, which by the time was sometimes thought to be massless, and also the gravitational field itself. These objects were found to be unstable under perturbations, which meant that eventually, after some time, they either leaked away or they collapsed into a black hole. So this last possibility is the one that we're going to be interested in, because when these electromagnetic entities collapse into black holes, they give rise to what we call Kugelblitz. Kugelblitz is a hypothetical black hole formed by the collapse of electromagnetic radiation. In principle, it is allowed by general relativity, and it has been considered in several contexts. For instance, in cosmic censorship hypothesis, in the study, they are candidates for dark matter. And they are also even used as the engine of a very speculative option for interstellar travel. Also, I've recently learned. Sorry, is there a problem? Because I'm hearing voices, but I don't know.
Yeah, I also hear that a bit too. Some kind of like mumbling. I think it's Evan. Sorry, can you put up?
Okay, sorry. No problem. It's just that I because there was also a problem in the beginning. I was like, maybe there is some technical problem I'm not aware of. Okay. All right. So as I was saying, like Kugelblitz are even considered a very speculative option for interstellar travel. They would be the engine. We were getting the energy from their Hawking radiation. And I've also recently learned that apparently they play some role in the third season of Anti-Umbrella Academy. So I guess I'm going to try to destroy their dreams as well. This is all classical, and the problem is that quantum effects were not considered in previous works, even though Wheeler, in his first work in 1955, already anticipated that they were probably going to be relevant. And the thing is that creating a Kugelblitz would involve electric field strengths that are very high. In particular, they would be over the Schwinger limit, which is the threshold over which particle creation is not exponentially suppressed anymore. So this means that we would be trying to concentrate a lot of electromagnetic energy in a very small region, and the electric field and magnetic fields in this region would be very high. And because of that, we would have particle-antiparticle creation, and this creation would not be suppressed anymore because of the intensity of the fields that we would be dealing with. So because of this would be a source of dissipation, because we would be trying to accumulate energy in a particular spherical region, but then we would have particles scattering away from that region where the light is trying to be collapsed into, right? And in this regime, the particle-to-particle creation is dominated by the Schwinger effect on one side, which is non-perturbative, and also the multiphoton Bright-Wheeler process, which is also perturbative. And we use a formalism that takes both of them together. So these are the two effects that we're going to be taking into account, and I will refer to both of them collectively as the Schwinger effect. And what we found is that the dissipation only due to the Schwinger effect, without taking into account other higher order effects, it's already enough to prevent the dynamical formation of Polo-Gómez with radii between 10 to the minus 29 and 10 to the 8 meters. And you'll see exactly where these bounds come from. The lower bound basically comes from being conservative and trying to not be very close to the Planck length. The upper bound comes from a specific calculation that you'll see. So how did we get to these numbers? So in order to arrive to this conclusion, we used a very simple model for the dynamical buildup of energy inside the spherical region, which would be given by this very simple ODE. Here, epsilon of t is the energy inside the spherical region where we're trying to accumulate the energy. Sorry, we're trying to get to form the Kugelblitz, and the dot denotes the time derivative. Then we also have r is the radius of the region, and f is the constant influx of electromagnetic radiation, which again we are going to assume to be constant because this is the simplest possible scenario, and also because we can basically upper bound any scenario. If you have some influx of radiation that is not constant, let me just pick the maximum of the influx that you ever had. I'm going to just use that one because, as you'll see, the orders of magnitude are so different, and that it is basically enough for me to just pick the supremum of your influx and still arrive to the same conclusion. So basically, in this 4 pi r square f, we just have the total influx of the total flux of electromagnetic radiation that the whole sphere is receiving, and then d of t is the dissipation due to the scattering of particle-antiparticle pairs, which we still have to determine. So, and for a Kugelblitz to form in the spherical region, the energy needs to reach the critical amount of energy necessary to form a Schwarzschild black hole, which is RC to the 4 over 2G. So we're just going to analyze this and see if it is possible for the energy to reach the critical amount. The problem, of course, is to estimate the dissipation. And the first problem that we face when we're trying to do this is the fact that the Schwinger effect is non-Markovian, while the ordinary differential equation assumes Markovianity. So perhaps the ODE is just not a possible model for this kind of process. But instead of just throwing away the simple model, we can try to bypass it by taking into account that the non-Markovianity is due to the back reaction of produced pairs on the electric field. So when you get more pairs, these pairs affect the electric field, and that is going to affect the ability of that electric field precisely to form more pairs. However, the dissipation that we care about is due to the pair production within the sphere. So what we're going to do is to take into account that the particles that leave the sphere, once they are produced, stop influencing the pair creation that we care about. So basically, if these particles are leaving the sphere after some exiting time, tau x, the whole process is going to reset after that exiting time. So we are going to assume for now that as long as this exiting time tau x is much smaller than the time scale capital T of the potential formation of the Kugelblitz, then it is safe to describe the evolution in a coarse-grained way that relegates the memory effects, the non-Markovianities, to the time scales that are below that exiting time. So in this case, what happens is that, again, as long as tau x is much, much smaller than capital T, then the continuous process is discretized into a Markovian sequence of non-Markovian processes, where non-Markovian processes would have a typical duration of tau x. But then because tau x is much, much smaller than T, then this discrete evolution of Markovian sequence of non-Markovian processes can be approximated by a continuous one, which is the one that would be reflected by the ordinary differential equation. Okay? So once we assume this, and again, we will check that this assumption is consistent with everything later on, then we can proceed to estimate the d of t. The d of t would therefore be the particle production that we get on an interval of duration tau of x, which would be the duration of the non-Markovian process. So to do this, we estimate the production using a Poisson-Teller electric pulse, which has this shape, right? It achieves the maximum in E of t, which is the electric field at time t inside the sphere, and then it is simply some adiabatic pulse that has infinite duration. Now, that has a characteristic duration of tau x. Later we'll see, well, first of all, notice the different time variables, because we have the t, which corresponds to the actual process of formation of the Kugelblitz, but then we have the tau, which is just the internal variable that is modeling the electric pulse with which we are estimating this d of t. This pulse is, I want to insist, is completely artificial. This is not the actual electric pulse going on in the sphere. This is just the pulse that we are using to estimate how much an electric field of magnitude E of t is going to produce. How many particles it is going to produce. So, and I'll justify later why we use this particular pulse and not another one. So now in the regime of approximation where these two inequalities are satisfied, which again I will check later that they are indeed satisfied, the adiabatic regularization, the normalization of the stress energy tensor lead to an estimation of the density, the energy density in infinity of that quantity, the quantity that we see here. This was calculated in a 2020 paper. And therefore, the energy that we're going to find that is dissipated is in particular in the sphere, just results from multiplying this number by the volume of the sphere. And then we get this number that is the estimated dissipation per unit time. So now that we have this number, we can just insert in the original ODE. And in particular, because we had an ODE for the energy, and we're assuming that we only have an electric field, a uniform electric field, then the energy density inside the energy density inside the sphere and the electric field are related by just the typical and the energy density is equal to epsilon 0 times the electric field square over 2. And therefore, we can just transform the ODE for the energy density into an ODE for the electric field. And this is the result that we have. And this ODE has the particular characteristic that it has a fixed point, which corresponds to this electric field. And this fixed point has the particular property that all the solutions converge towards this fixed point. Okay? All solutions that start with a positive electric field, because this is just the magnitude of the electric field, are going to converge towards this. So the condition for the formation of the Kugelblitz has to be that because this is the field that is asymptotically reached by the electric field, and since we're assuming that we are going to form the Kugelblitz building up the energy, so we start from 0. The condition has to be that if we are going to eventually reach e to the infinity and we are not going to go over it, then for the Kugelblitz to form, the critical electric field associated with the critical energy that needs to be reached has to be in between 0 and this e to the infinity. That is, the condition is that this asymptotic field has to be bigger than the electric field associated with the black hole, which again is the electric field associated with the critical energy that we need to form the Kugelblitz, which can be calculated like this. It's just a particular phi over r, where phi is this electric potential. So now, in particular, in particular, to estimate, to make estimates about what this e to the infinity is, see that here we have the influx, but also we have tau of x. So we need an estimation of the exiting time to make estimations about the influx at all. And because the particles, antiparticles that are produced are ultra-relativistic, we are basically going to assume that the exiting time is just the radius of the sphere over c. So once we have that, we are in position to use this condition to make estimations about what is the necessary influx to form a Kugelblitz. And what we find is that, well, first of all, we can make estimations about the intensity, and then the influx, we see that is bigger than this quantity, which is 10 to the 83 watts per meter over r. So it depends on the radius of the Kugelblitz. But so this means in particular that if we want to form a Kugelblitz of a radius of 1 meter, then we're going to need an intensity that is bigger than 10 to the 83 watts per meter. Now, to see how big this is, you can compare it with the highest laser pulse intensity that we have nowadays, which is 10 to the 27 watts per meter square. Okay. So you see how we have like almost 60 orders of magnitude of difference. We can also make estimations about the energy.
Have you compared that to the total energy in the universe? Or,
Well,
or the
no, because
observable universe?
it's intensity.
Yeah.
So for the energy, I was gonna do it now.
Right.
But I mean, I don't think if you compare it with the universe, I think you're still it's gonna be there. But I think probably the universe will win. But I haven't done the calculations.
Right.
But in the case of, well, we have the power. We can just multiply with 4 pi r squared, and then we get this relation. And again, for a cool bits of 1 meter, one would need a power that is greater or equal than 10 to the 84 watts, which can be compared with the power output of the brightest quasars, which is 10 to the 41 watts. To your question, Jermaine, I don't know, because it depends on the density of objects that you assume. So I don't really know what
And
is a
what,
fair estimation
and
of
I
the
suppose
total
what you
power.
count as the observable universe as well.
Yeah, I'm counting as just the overall universe. But yeah.
Quick question, Jose.
Yes.
Why do you have? Why are there different units? Watts per meter versus watts per meter squared?
Oh, sorry. Yeah, the intensity is watts per meter squared. So once you put here, I don't know, like 1 meter, then you would get the intensity is bigger than 10 to the 83 watts per meter squared. Like
Okay,
these are units of intensity.
Oh, the second one is R times. Sorry. Okay, it's right. Sorry. I see now.
I'm sorry. Yeah, I think I said out loud the intensity would have to be bigger than, at first, 10 to the 83 watts per meter. That was my mistake. Watts per meter squared. Yeah.
All right. Thanks. Go on.
No, you're welcome. Yeah, sorry for the mistake. But yeah, again, this calculation is as simple as just taking into account that this is the black hole electric field that we need. And then here we just input this number, and well, we have to add the extra assumption that the exiting time is this, and we can just obtain conclusions about how big the F has to be, right? And the fact that because we have this difference in the orders of magnitude, that's why I told you before, oh, you might have a fluctuating influx. It doesn't really matter to me. Just pick the biggest one, which is obviously going to lead to an upper bound to what's the energy buildup that you can get, because there is no oscillating here, so there is no resonances or anything. And with that, I can already use that. I'm still gonna find something ludicrous. So that's why I said, well, it doesn't really matter that you don't have a constant profile. Regarding the approximation of the exiting time, we'll also justify it later. You'll see that I'm using a number of approximations, and and I'll go to that later. Just for now, I'm just putting them on the side, and I'll talk about them later. So with these numbers, what we see is that, well, for reference, if we consider here, of course, we have to evaluate it for different radii. I just put the example of the 1 meter because it was the obvious one. But then you can compare it with the Planck length. For the Planck length, you would need a ludicrous intensity, although the power would have to be smaller. And then, well, you also have on the other side of the spectrum, the radius of the observable universe is still 10 to the 27. You still need, you even for such a radius, and the intensity would still have to be like more than 20 orders of magnitude bigger than the highest laser pulse intensity that we have achieved. In any case, within this, what we see is that with this calculation within these scales, we can essentially rule out the possibility of the formation of a Kugelblitz, because of the abysmal difference between the conditions that it requires and the conditions that are realistic available. I have to insist in our current universe, both in the lab, which is the comparison that I gave with the highest laser pulse intensity, and in astrophysical scenarios, which is the comparison that I gave with the output of the quasars. Now, I insist that all I said is in our current universe, because I'm not ruling out the formation of Kugelblitz from some physical law. I'm just calculating what are the conditions that are necessary, and I'm seeing that with the conditions of our current universe, we don't really have any sources that are that powerful or that intense. But of course, I don't know if this is also true for the very early universe. So there might very well be that, I don't know, even primordial black holes, some of them were formed in a very early radiation field universe where these conditions were actually met. So I'm not saying anything about that. In fact, it would be very cool if indeed that's the case, that some primordial black holes are actually cool blitzed. But I'm only talking.
I see it as kind of reminiscent of Dyson's analysis with regard to graviton detection, where he doesn't have it's not necessarily a no-go theorem, but just analyzing certain conditions under which it seems practically impossible to
exactly.
Yeah.
But I'm only using the conditions of our current universe to argue that. That's why I want to clarify that I'm saying nothing about the early universe.
Does that mean that it could be possible that some of the existing black holes in the universe were formed from light in the early universe? That could be.
Yeah, I don't see any reasons why that wouldn't be the case. I mean, I think it's actually a very exciting possibility. I haven't analyzed it, but I think it's in principle, as far as I know, it should be possible. It would be possible, maybe. Again, we would have to analyze what are the conditions in the early universe and see if they would meet the conditions necessary for forming a cool bits. But also you have to take into account that the conditions are the setup would also be different, probably because in the very early universe you would have a radiation field universe. So perhaps the setup shouldn't quite be the one that we're considering here, where you have to focus the radiation. But actually, you would probably already have some density of radiation there, and what you would have to see is if the radiation that is already present maybe will by the action of some fluctuation of something. So maybe some fluctuation of density, maybe the density reaches the critical. So what I'm saying is also that I don't think, if I had to analyze that for the very early universe, I'm not sure if I would use the same setup or the same method that I'm using right now, because also the conditions are different. So I think probably the setup would have to be different, because here I'm focusing I'm using an argument that is based on focusing radiation, but then in other conditions maybe you wouldn't even have to focus. Right? Yeah, I don't know. But again, not a setup that we have analyzed. Okay, so far so good. These are basically our conclusions, except with the bounds, because you'll see that the bounds come from the you'll see that the bounds are going to come precisely from the assumptions that we have made and the limitations that they have. So yeah, if you all believe me up to here, I think it's already a success, because I've used arguably a very, very simple model, right? And many of you would probably would say, well, you have to see exactly to what extent all the many approximations that you used are valid. And so that's exactly what I'm going to do now. I'm going to go through the main approximations that I used. I'm going to analyze them. I'm going to argue why I think they make sense. These are the main approximations. If you think I forgot one, you can tell me. So the first one is that I assumed a Minkowski background. This is particularly surprising because I'm analyzing black holes, right? So it's like, okay, what? If you're analyzing black holes, why are you using Minkowski and assuming a flat spacetime? The second one is that I considered a uniform electric field inside the spherical region where I'm focusing the radiation. That is also obviously not a realistic approximation, because in general you'll have lasers. So of course I'm going to have fluctuating electric fields. I'm going to have magnetic fields. So what happens with that? Why is your approximation of a uniform electric field a good one? I'm also modeling the dissipation as a Markovian sequence of short-norm Markovian processes. I already explained this, and I already said what are the conditions in which this approximation should be good, but we have to check that those conditions are effectively are met. And then only if I have time, which I think I will, I'm also going to talk about why I chose the specific electric pulse profile that I chose, the Pochel-Teller pulse, to calculate the dissipation. And I'm also going to justify the estimation that I made about the exiting time. Okay. So, well, first of all, to see how it makes sense to use a Minkowski background, first recall that we had this condition as the condition necessary to reach the black hole electric field. Right? And the e to the infinity, the asymptotic electric field, has to be bigger than the black hole electric field. However, this condition, we can rewrite it as simply this condition which would be the condition for the necessary intensity or power needed to reach a particular electric field, E, right? So this is not related to the black hole anymore. This is just speaking about what is this is going to give me conditions for my setup to be able to reach a particular electric field. No, because the orders of magnitude that I had when I put here EBH are so different from the ones that I can actually reach. The argument that I made before actually indicates that not only it is not realistic to reach EBH, it is not related to reach anything that is close to EBH. If instead of a black hole electric field, I pick some electric field that is, I don't know, 5 orders of magnitude below that, I'm still going to be many orders of magnitude away from being able to reach that. So what we see is that the dissipation, due to the Schwinger effect, guarantees not only that an event horizon will not form in the region, but it also guarantees that we are well within the Greek gravitational field approximation that is compatible with a flat spacetime. Essentially, what we are seeing here is not only that you cannot form black holes with light. Essentially, with our model, what you can see is that you cannot really curve spacetime in a significant way with light, right? Because this is because light is going to disperse away, or the energy carried by the light is going to be dispersed away by the particles and antiparticles, and this is going to prevent you from accumulating enough light to cure spacetime in a significant way. So that's why it
Does that
makes
have
sense.
relevance for the gravitationally induced entanglement proposals, where, say, you wanted to look at gravitationally induced entanglement between light and, say, a gravitational source mass? That if you can't,
can you repeat again the question? Sorry.
In terms of the relevance of that point of not being able to curve spacetime for, say, trying to witness an extension of the gravitationally induced entanglement proposals, but with light as one of the gravitational sources.
Oh, I wasn't aware of this proposal. Yeah, I mean, for me, that would definitely, this would probably, I mean, it depends on exactly what is the setup, because also you have to take into account that.
Like, I think, could you still measure, say, I suppose there's no such thing as a Newtonian gravitational field for the light.
No, I mean, in principle, what I'm saying also is that, yeah, that the gravitational effects that are going to be induced by light in general are not, no, you're not going to be able to accumulate enough light for them to be significant.
Right.
But of course, that there are so many ambiguities about the words that I'm using right now. So, like, for instance, for me now, significant means that it affects the fermions, because really,
it seems to suggest it would rule out using light as an active gravitational mass.
Yes, but it depends on for what. Because for instance, if again, that's why I clarified significant for me here means for the fermions, right? Because really, the reason why I say that I'm using a Minkowski background is because I'm just assuming that the fermions leave with no gravitational influence from the light's side, right? But I don't know, depending on the precision of this setup that you're telling me. I mean, I would doubt that they are able to measure the influence of that one laser beam has on another laser beam. I don't know the precision that they have, and I don't know the intensities that they are managing, and also I don't know the conditions of the laser, because the thing is that you also have to take into account the conditions in which the Schwinger effect is enhanced or suppressed. So, for instance, we do know that a single electromagnetic wave is never going to be never going to produce particle and antiparticles, right? So if you have a single electromagnetic wave that is very intense, of course this will have to be ludicrously intense, right? But if it is very intense, you're not going to have any Schwinger effect hindering you from getting more and more intense. That's what I'm saying. So I guess it also depends on the conditions of the lasers that this proposal uses. But my bet is that in general, this would be very complicated. Yeah, I mean, again, I haven't seen the proposal, so I'll have to see the specifics, because I'm pretty sure that whoever, I don't know the proposal, but whoever did it, I'm sure they are aware of the fact that that when you concentrate electric fields and electromagnetic fields too, because for instance, the Schwinger effect is enhanced when you focus lasers. So actually, the electric field that you need to reach for particle-antiparticle creation to be significant is actually a lower threshold than when you only have electric fields. So actually, when you have lasers that are being focused and they are colliding, this is a more advantageous situation for the Schwinger effect. So I'm sure the people that are working on this know these things probably better than me, and they probably took that into account. So again, that's why I'm saying I don't want to say anything about that proposal because I don't know it. I would like to see it. So if you know where to find it,
I can email you a couple of papers on that.
Yeah, that would be nice because that way I can see it and maybe I can tell you a bit more. But I'm pretty sure they took it into account and they made the calculations appropriately. So, for instance, if they have as a pair of lasers and they have very good coherence conditions, these are conditions under which the Schwinger effect can be suppressed. They are not conditions that I took into account because I think that the thing that you're going to have so many lasers in a very, very coherent situation is extremely difficult and unlikely. But unlikely from astrophysical, from the perspective of the physical scenarios, and very, very difficult in the case of the lab. But yeah, these are conditions where the Schwinger effect can be suppressed. So maybe they set themselves precisely in this setup, or simply they just have enough precision to measure how much one beam of laser is affecting the other beam of laser. So yeah, again, I will have to say I'd love to read about it when you if you send it to me and we can discuss to what extent these effects can have.
Yeah.
But here in particular, what I'm referring to is the fact that if you're trying to accumulate light in this manner, right, when you're basically either colliding lasers or trying to accumulate light in some way, you're not going to be able to accumulate enough for them to cure space-time in a significant way for the fermions, at least, in the sense that the fermions are going to escape the region as if essentially there was nothing inside. Okay? So yeah, that's the reason for the first assumption and why we still use a Minkowski background, even though we're talking about black holes. The second approximation is the one that is related to the things that I was discussing right now, precisely, which is the uniform field approximation. So to discuss it, we can wonder what happens if we lift it. So what happens if the electric field is, first of all, time dependent, right? Which is something that I mean in the specific non-Markovian process, right? So in this case, the particle production is enhanced, right? So this is a scenario we don't have to worry too much about. Then what happens if the electric field is space dependent? Well, this one is a little bit trickier because particle production does get suppressed in this case. However, it only does so at scales that are below the per-formation length. Okay? And for the electric field strength required to form a Kugelblitz, this per-formation length is of the order of 10 to the minus 22 times the radius of the Kugelblitz. That means that essentially for Kugelblitz that are small enough, we're gonna need radiation of a wavelength that is very, very small. Essentially because the fluctuations of the electric field are going to be essentially of the order of the wavelength of the radiation that we're using. And so this means that only for radii that are over 10 to the 9 meters, we can approach a wavelength that is reasonable, which is, for instance, 10 to the minus 13 of gamma ray bars, right? Just for reference, and to see why 10 to the minus 22 or anything below that is a ridiculous wavelength, 10 to the minus 21 meters is the shortest wavelength that has ever been observed, right? So on top, I'm taking into account also that I'm using, for instance, as a reference gamma ray bars, because whatever this radiation that we intend to use to form the Kugelblitz is, we also need it in high quantities, right? Because we need to also reach this threshold of energy to form the black hole. So anything that we found in a very scarce way, it does not make sense to use it as a source for this. That's why I said, okay, let's consider gamma rays because it's the only thing that even if it's in very particular scenarios, you can get those in sufficient quantities, right? But it's only for radii that is over a particular threshold that, as you'll see, also because of other reason, it's a size of radius that we have excluded from our conclusions. So we're safe on that side. And then finally, you say, okay, you're using radiation, so you definitely have a magnetic field. What happens there? But if you take into account the presence of the magnetic field, then the pre-production is enhanced, especially in scenarios with focused radiation and or multiple sources, which is exactly what I was saying to Jermaine before. Of course, here I have to say that the magnetic field in general enhances the production, except when it is orthogonal to the electric field, and because in that case it is going to suppress it, and in particular it cancels it out when it has the same magnitude of the electric field. This is exactly the reason why for a single electromagnetic wave you would have no Schwinger effect. It's because in that case the electric field and the magnetic field are orthogonal, and a single plane electromagnetic wave, I meant. In that case, they are orthogonal, they have the same magnitude, and that's why there is no Schwinger effect. But of course, in general, if you just mix a lot of radiation together, that's not going to be the case. So in general, the electric field and the magnetic field are going to contribute together, and the magnetic field is going to enhance the Schwinger effect. Unless, again, you have some sort of very, very high coherence and you figure out how to do this in a more general scenario. That's why I said that I think this scenario, we rule it out because it's very unlikely. But in principle, one could. If we are smart enough, maybe we can work our way out of it. But in general, without taking into account this case, the conclusion is that considering a uniform electric field should lead to an underestimation of dissipation, because actually lifting up that condition and considering more general scenarios, what we have just seen is that in those cases, the particle production would be enhanced. So actually, by considering a uniform electric field, we're just underestimating the amount of energy that we need to form the black hole. Finally, let's check that we are that we perform the Markovian approximation is justified. So we just have to check that the tau of x and the exiting time is much smaller than the time scale in which the Kugel blitz forms. So the tau of x we already estimated as r over c. So we just need to estimate the time of formation of the Kugel blitz. But of course, this can be lower bounded by the time it takes to form the Kugel blitz without dissipation at all. So we have that the capital T is greater or equal than just the energy, the critical energy of the black hole over 4 pi r squared f, right? And this is just a particular number. And so what we see is that, again, using that the exiting time is approximately r over c, we have that, and in particular, it's upper bounded by it. We have that the quotient of the exiting time over the time scale of formation of the Kugel blitz is upper bounded by that quantity, which is, again, approximately this quotient. So what we see is that the power that we need, at least for the exiting time to be comparable to t, it has to be of the order of 10 to the 52 watts, which is, again, already 10 orders of magnitude above the power output of quasars. Right? So again, we need a very, very high power for these two quantities to be comparable. So in general, we are safe because I don't know if we put here the power of quasars, then here we would have at most 10 to the 41 watts. So this quotient will be upper bounded by 10 to the minus 11. So this is a quantity that makes it reasonable to assume that tau x is much smaller than t, capital T. And the second part is that to make the calculations about the Markovian approximations, we did so under a regime of approximation in which these two inequalities were satisfied. We're going to analyze that they are indeed satisfied. The first one is actually simply a requirement that the electric field strength that we are dealing with needs to be much larger than the Schwinger limit. Of course, this is necessary because we are working already in all our calculations, we are assuming that we are in a regime in which the particle-antiparticle creation is not suppressed. And then the other one can be rewritten as something like this. And what we see is that both inequalities are satisfied whenever the whenever R is between these two quantities, taking into account that we saw before that the EBH times R equals to phi. And again, this is actually something that comes out of these two inequalities specifically. But then this is not exactly the number that comes out of them. It's a little bit more conservative because we don't want to be close to the Planck length because we don't know what happens there. And this would be exactly the inequality that I gave you in the beginning of the talk. And now, since I still have time, so I don't know if you want me to keep going with the two extra things that I wanted to talk about, or you want me to skip and maybe leave some time for discussion?
I'm fine. You can keep going.
Okay.
Yeah.
Perfect. Okay, so then the other thing is the choice of electric field pulse profile. I used a Polo-Gómez pulse, and the reason for using this is just that it is adiabatic. And because of this, the tails have a negligible impact on the estimated particle production. This is good because it means that basically any other smooth big pulse would have yield not exactly the same number, but the same order of magnitude of particle production. And moreover, if you don't use a smooth big pulse, if you don't use something that is adiabatic, then you're going to actually have extra particle production, which is going to overestimate the particle production. So this is, again, just the most conservative choice to estimate the particle production that we have in each one of the non-Markovian bits of our process. And you could have used another adiabatic pulse, but we already had this one, and calculations performed with other adiabatic pulses should not alter the order of magnitude of this. And regarding the estimation of the exiting time, well, here, the thing is that we are, again, working under the assumption that these two inequalities are fulfilled. And then the velocity of the fermions that are produced via the Schwinger effect can be calculated from their energy. So in particular, the velocity is given by this. But it turns out that with these two inequalities, MC is much smaller than the electric charge times the electric field times the exiting time. So because we're in this regime, this quantity is much, much smaller than 1, and therefore V is essentially the velocity of the fermions is essentially just the velocity of light. And then if one considers that the particles are produced at random positions and with random directions inside the sphere, then on average, the exiting time is indeed the radius of the sphere over the velocity of the particles, and this is approximately R over C. Of course, there will be particles for which the exiting time is going to be 2R over C, and there's going to be particles for which it's going to be 1/3 of R over C. But then again, on average, it's just going to be R over C. Also, again, as I said before, the gravitational attraction exerted by the confined radiation and the scatter fermions is neglected. And one way one can see that this approximation is justified is by comparing the velocity of the particles with the escape velocity. And it is indeed something, the escape velocity is much, much smaller than the velocity of the particle. And that is all. So the message is, all in all, that I want you to take home is that, well, Kugelblitze with radii between approximately 10 to the minus 29 meters and 10 to the 8 meters are impossible under the current conditions of our universe due to the dissipation via the Schwinger effect. This means, in particular, because sometimes our experimentalists can get some crazy ideas, we should not spend funds on trying to create microscopic black holes from high concentrations of light. And also, for me, maybe the most interesting part about this work is that it underpins the importance of the role of that quantum effects can play even on the context of strong gravity phenomena, but without going to the quantum gravity realm. Right? Like here we are basically studying a scenario that belongs to strong gravity phenomena, but we are discarding its possibility. We are sort of regularizing the Kugelblitze. We are regularizing that particular singularity, seeing that it's not possible, using only quantum field theoretical effects, and without necessarily going into the realm of quantum gravity. And maybe this result can be generalized to other collapse scenarios. In fact, my collaborators and I, we are already studying what happens in the case of gravitational waves. If we can form black holes with gravitational waves, because there are several works that already analyzed this and found that in particular scenarios that are not very realistic, you can form them. But we are trying to see if we can apply the same techniques or similar techniques to see if black holes can indeed be formed from gravitational waves, or if we're going to have quantum effects playing a role from quantum effects coming exclusively from linear quantum gravity.
Like a linearized gravity version of the Schwinger effect.
Exactly. Yeah, that's exactly what's going on.
I was going to ask that actually, whether
it's a simple. I mean, it's not very studied, and there's only like a couple of works about it. But we are working on the formalism because it's very analog. It's very analogous. It's not
any preliminary results, as in with gravitational radiation, would it be similarly impossible?
We still don't have them because we had a period in which we couldn't work on this at all, and we started working this December. So we don't have any preliminary results, but I'll let you know.
Right. I'm curious about that.
Yeah, but it's essentially the same. It's a very similar setup and the same techniques. Sort of.
Yeah. So you would expect a similar result in terms of an impossibility within some certain.
That I don't know, because the thing is that the magnitudes are very different. The charges are different. So I
suppose the Schwinger effect could be so much suppressed compared to electromagnetic radiation.
Exactly. And that's why we are not sure yet. We tried to do some like preliminary estimations, but we were not convinced about the way we basically we try to wave our hands about, if this is the quantity that is analog in this case, this, right? And we try to do some kind of very informal estimation using that sort of logic, but we weren't convinced about the results, the estimations that we were getting. So yeah, I don't want to say that we have any preliminary results, but we'll see.
Yeah. I'm wondering if you could also use in our papers on applying quantum optics models to gravitational waves, whether you could use
what again?
Whether you could use the models, some of the models that we worked with in applying standard quantum optics models to gravitational radiation and looking at scattering processes in that context.
I think essentially it is essentially the same. I mean, in the end, we're going to be using linearized gravity, and we're going to get an effect that is essentially. The problem is that, I mean, we cannot use exactly quantum optics, depending on what you understand by quantum optics, because for me, sometimes quantum optics is just like applied QED. But in the sense in which you don't need to deal with the full QED formalism, since the Schwinger effect is
using the simpler quantum optics toy models kind of thing.
Right, but the problem is that we do need to go a little bit more in depth in the QED formalism, because the Schwinger effect does not really show up in standard quantum optics. Really, you need a little bit more of the full-fledged formalism to see it. So that's why, like, for me, it would be the same. It's basically using the analog of QED when you have linearized gravity, right? But it's not the same as just using quantum optics, because we do need to go a little bit further.
That makes
QED
sense.
But the logic is the same. It's just to use some strategy that we use for electromagnetic field to analyze a problem related to the gravitational field. Yeah, in that sense. Right. And well, before finishing, I also wanted to talk about one little thing, is that in case someone saw it, Abraham Law wrote a comment about our work, to which we replied. In case you want to say it, because he claimed that we ignore gravity in our calculations, and gave two examples where light would form from black holes. So our reply is essentially that we are not quite we were not convinced by his counterexamples, because they don't apply to the regime where we do all calculations. Because gravity was not ignored in our work, it was neglected but we justified in which regimes it was possible to neglect them. And also, the first example that he gives shows how accumulators could form from over densities in the early universe. But I already said that in the original paper we see that our results are only applicable to the present day universe. So that counterexample doesn't apply. And then the second example that he gives shows how accumulators could form with the radiation below the Schwinger limit. So this is a regime where already the radiation that you have doesn't lead to an electric field that is over the Schwinger limit. And this is a regime that I mentioned before. Like, you wouldn't have the Schwinger effect here. but that would be the black hole is large enough. He gives an example of a black hole of the size of our present of our observable universe. But this is a range of sizes that we explicitly discarded. So basically, his counterexamples focus on regimes that we already discarded. And the full reply, if anyone is interested, is can be also found in arXiv. I just wanted to comment on that side in case anyone saw our work and saw that you had a comment. And that's all.
Perfect. All right. So thank you very much for that interesting talk. Do we have any, apart from the ones that were asked during the talk, do we have any questions now?
Yeah, I have a question. So the electric fields we're looking at are beyond the strong enough so that they can induce a Schwinger effect, which is a non-perturbative effect.
Mm-hmm. Yeah, that's right.
So I'm wondering, I'm sorry, I might have actually missed which part of the talk you actually said. But how do you justify ignoring the stress energy contributions from the massive electronic field generated by the Schwinger effect, and also the Hamiltonian contributions of the interaction term in the QED Hamiltonian? Are they small enough to ignore, or?
So you're asking, am I discarding that the fermions that are created itself? I'm neglecting that they affect to the gravitational field. I'm neglecting the gravitational field created by the fermions themselves. That's what you're asking.
Yeah.
And so I I didn't mention it. But the idea is essentially that you would not. I mean, you would have to somehow confine them. Excuse me. Here because the exiting time is much smaller than the time scale in which the Kugelbits forms. Essentially, the fermions are not gonna. The fermions, the energy of the fermions is not gonna. It's not gonna lead to some sort of buildup of energy, because they're gonna escape the region where you're trying to accumulate the energy before they can lead to buildup that is big enough. Perhaps it would still make sense to evaluate exactly what's the energy that they have, like the energy of one batch. Let's say the fermions. Like if the fermions that leave in the amount of time that is equivalent to the tau x, right? The exiting time before they leave is the energy that they have enough to yield a gravitational attraction that is significant. And we have not made this calculation actually, and I have never. I gave this talk already several times, and I never got this comment. So it's actually a very interesting point. I will have to make the calculation. My bet would be that it is not significant, of course, because that would go against my result. But yeah, I guess that is a calculation that you have to do to make sure that you're not already creating the Kugelblitz with the fermions that you produce, right? Yeah, that is a very good point. And no, I haven't mentioned it. I actually haven't done the calculation. But I mean, the calculation has to. It cannot be enough because if that was enough, then essentially it would mean, because the energy of the fermions is smaller than the energy of the radiation, the radiation that went into the sphere in that same period, the tau of x. That would mean for the fermions to form the black hole, that would mean that the radiation that you put inside the sphere in that same period was already enough from the black hole. But that would go against the regime in which we're working, which is that the exiting time is much smaller than the time scale of the Kugelbits. which is again a scenario that is in principle possible. Like if you already have all the radiation, like okay, so for instance, if you have the following setup in which you already have a pulse of radiation that has all the and it's in a very it's a very thin pulse, right? And that already has all the radiation that you need to form the black hole, and you basically, I don't know, you make two pulses like that, or almost all radiation, and you make two pulses like that collide and they form a black hole. I have nothing to say about that scenario, but that requires a lot of energy. That requires a lot of energy, yeah, and a quantity of energy that, from our estimations, is unrealistic. So yeah, that would be my reply. We have not taken I did not mention it explicitly, but I sort of implicitly discarded it. Yeah. And you mentioned another sector. I don't know if that convinces you, by the way, or
it does actually convince me, yeah, because obviously we need to conserve energy. So,
and then you mentioned another part, but I didn't hear it or understand it. I don't know if did you mention another sector that we were ignoring, or that was all?
No, I think that was all.
Oh, that was all.
I'm
Okay,
very tired, so I have to remember now. But
okay,
yes.
Sorry.
But thank you.
Well, thank you for the question.
Right. Any further questions? I mean, I asked mine during the talk, so if that's everything, then thank you again, Jose, for coming by to give the talk. It was really interesting.
Thank you, German, for inviting me, and thank you for those that joined from. I don't know if Nico is in Australia, but if you are Nico, thank you for joining because I know it's very late.